There are several reactions of alcohols that we will consider in this chapter. The first one is the dehydration. Dehydration, as the name says, it's the loss of water. And whenever you are losing water, you are going to create an alkene as a product. Always, whenever your product in an organic reaction is an alkene, the reaction is called elimination reaction. So this one is going to be an elimination reaction, and an elimination reaction by definition is a reaction where you break two sigma bonds and you form a pi bond, so your product is going to be an alkene. So the alkene here is going to be the product, meaning that your product is going to have a double bond. So what I am doing here is that I am losing water, and water is going to be in a form of a hydrogen and an OH. So I am going to lose a hydrogen and I'm going to lose the OH. The hydrogen that I'm going to lose is called the beta hydrogen. If you look at any alcohol in there, for example, any alcohol, primary, secondary, or tertiary alcohol, normally the carbon that is connected to the OH, we call it the alpha carbon. And the carbon next to it, which is adjacent to the alpha, it's going to be beta. Here in this example, it's one carbon. It can be more than one carbon. If there's another carbon on the side, then I would have two beta carbons. But here, I only have one beta carbon that I am showing in there. So the loss of water is going to proceed as such. You are going to lose the beta hydrogen, and you are going to lose the alpha OH, okay? So that is it. You are going to lose the alpha OH and you're going to lose the beta hydrogen. So I will be breaking those two sigma bonds that you are seeing here. So I'm going to break the sigma bond between the hydrogen and the beta, and the sigma bond between the OH and the alpha. And whenever you break two sigma bonds, you will form a pi bond between the carbon alpha and the carbon beta, because this is where you lost the sigma bonds in there, just to compensate the loss. So your product is going to be an alkene. So always, whenever you want to form your alkene, see where is your alpha hydrogen, where's your alpha OH, where's your beta hydrogen, and they create the alkene in there. So your product here is going to be alkene. And that is, we call this the major product. And it is the product that exists at a higher percentage. This is what major is. So by definition, breaking two sigma bonds will form a pi bond. So if you break two sigma bonds, implies you will form a pi bond. And any dehydration reaction, since you are losing water, everything that you're going to lose is not going to just disappear. You are going to see it in the product side as well. So your byproduct is going to be, this is byproduct, is going to be water. And the major product, the organic major product, is going to be the alkene. The alcohol that I start with can be primary, can be secondary, or can be tertiary in there. Now, the reagents that I use in order to proceed with a dehydration reaction needs to be an acid. And the acid is either phosphoric acid or sulfuric acid. Also, the temperature plays a very important role in this reaction. The temperature has to be high temperature. So the temperature that we're looking for is 180 degrees. The reaction does not proceed without the acid. So the acid here in this reaction is considered to be a catalyst. And it is a must for this reaction to happen. If the acid is not there, then the reaction will not proceed. So here you're not going to get an alkene, so we would say this is a no reaction. So two things that contribute to this reaction here in the alkene formation: the presence of the acid and the presence of the temperature. If any of those were missing, then your product will not form. Let's have an example. So I do have an alcohol in there. This one is a primary alcohol. Why it's a primary alcohol? Because see, you have the carbon that is connected to the OH, and next to it you have one carbon, so this is why it's a primary alcohol. This is again a dehydration reaction, so the first thing I need to start with is to locate my alpha carbon, and the alpha carbon is the carbon that has the OH. Now, adjacent to the alpha, there's the beta carbon. So please start by locating your alpha and your beta carbon in there. From the beta carbon, I want my beta hydrogen. Here I have two beta hydrogens. I'm just going to use only one. You're not going to use two because these two beta hydrogens are the same. So we're just going to pick one. The rule for the dehydration is that I am going to lose the alpha OH and I'm going to lose the beta hydrogen in here. So this means that I am going to form a double bond between the alpha and the beta, okay? I am starting with a structure that is a 3-carbon chain. Let's highlight the carbon chain that we have. Let's use this color. So let's highlight the carbon chain. This is the carbon chain. It's a 3-carbon chain. So here you go. This is going to be my 3-carbon chain in there. I'm not doing anything. And my alpha and beta were between those two carbons. I'm going to number those as carbon 1 and carbon 2. So the alpha is on carbon 1, the beta is on carbon number 2. So I am expecting that my alkene or the double bond is going to be between carbons 1 and 2. I'm going to lose the alpha OH, so that is my first sigma bond over here. And I'm going to lose the beta hydrogen, which is the second sigma bond in there. So those two, I'm going to lose them. And I'm going to make my alkene. This is the only alkene that I'm going to form. So that is going to be my alkene, plus of course my byproduct, which is water. And that is going to be my major product. This is an example of a secondary alcohol. The type of alcohol does not matter in this reaction, but it actually dictates how many products, alkene products you are going to get. So with primary alcohol, because I only have one type of beta hydrogen, I'm just going to get one alkene. But with secondary alcohol, if the R's are different around the OH, then you have different beta hydrogens. Then you are going to get different alkene products. So I'm going to start by locating my alpha carbon in there. The alpha is not going to change, but around the alpha, I here have two beta carbons. So I'm just going to call this beta 1, and this one is going to be beta 2. The betas are different because beta 1 is a CH2 and beta 2 is a CH3. So that is going to be a hydrogen here, and this is the 3 hydrogens. I only want, all of these 3 hydrogens are the same, so I'm just only going to pick one of these hydrogens in there to eliminate. Okay, I do have the elimination condition. So I'm going to start with, since 2 different beta carbons or beta hydrogens, then I'm going to end up having 2 alkenes in there. So this means that elimination can happen, and I can take the alpha OH and the beta 1 hydrogen and make the alkene over here. Or I can take the alpha OH and beta 2 hydrogen and make the alkene there. So I'm going to end up getting 2 alkene products. So that is the first alkene product. If I lose the alpha OH, and if I lose the beta 1 hydrogen, then I'm going to end up getting this alkene product. Plus, if I lose the alpha OH and if I lose beta 2 hydrogen, then I am going to get this alkene product. Guys, please notice, it's very important that I am not adding any carbons. So I have a 4-carbon chain. I am ending up with the 4-carbon chain. What is different here is the position of the alkene that I am forming. The alkene can form either between those 2 carbons or between those 2 carbons, because this is where the location of the beta hydrogen is. Okay, so my products, if I want to name those, my product here is going to be 2-butene. And this one is going to be butene, not 1-butene, it's just the butene in there. Now, every time, whenever you have more than one organic product, one of them is going to be major, meaning that it exists at a higher percentage, and the other one is going to be minor. It means that it exists at a low percentage. Okay, so before going into that, just let me refresh your memory about the types of alkenes that we've talked about earlier in chapter 12. And we said that with alkenes can be either monosubstituted, a disubstituted, a tri, and a tetrasubstituted. By definition, the more carbons around the double bond. So the more carbons around the double bond, the more stable the double bond is, so the more major it is. This is the rule. And for the disubstituted alkene, there are 3 cases in there where you can have a double bond and 2 carbons that are connected to 1 carbon, or you can have the 2 carbons on adjacent carbon. In this case, you will have cis and trans. Trans is always more stable than the cis. Why? Because you need the groups to be far away from each other so that they won't repel each other. So that is going to cause this structure to have less energy. So less energy means more stable, because energy and stability are always opposite. So please put this as a note that trans is more stable than the cis if you have a disubstituted alkene and you're able to make the cis and the trans. Trans is always the major, and cis is always the minor. When we say that a compound is stable, this means that it is the major product. So as you increase the number of carbons around the alkene, as the stability is going to increase, this means that your compound is going to be major. So for this example over here, to determine which one is major, which one is minor, we're going to do exactly the same thing. We are going to highlight the double bond and see the degree of substitution that we have. So for the first one, it is a disubstituted alkene. So this one is a disubstituted alkene. And this one is a monosubstituted alkene. So it is a monosubstituted alkene. And again, you highlight the double bond and see how many carbons it's connected to. It's connected to 1 carbon here. I don't care about the other. But the connection here is 1 carbon and then a hydrogen and then 2 hydrogens here. So this one is a monosubstituted. And this one over here is 2 carbons and 2 hydrogens. So it's a disubstituted alkene. The more substituted the alkene is, the more major it is. So just put this as a note, that the more substituted the alkene is, the major it is. So this means that this disubstituted alkene now is going to be the major product, and this one is going to be the minor product. Every time you have more than 1 products, you should have only 1 major, and the rest are going to be minor products. Let's have another example in here. So as I said, the more carbons around the alkene, the more stable the alkene is. This is always the rule. So the question is over here, you are having the cyclohexanol and substituted cyclohexanol. This is a dehydration reaction. You are eliminating water because of the temperature, because of the acid. So the question is to draw all the elimination products and label the major and the minor. So we're going to do exactly the same thing. You are going to locate where your OH is, and that carbon, you're going to call it the alpha carbon. And then you're going to look at the adjacent carbons in there. So I do have here 2 adjacent carbons on the alpha. You have to consider them all. So that is going to be beta 1, that is going to be beta 2. You can number them anywhere you want. It doesn't matter. These are different because beta 1 has 2 hydrogens on it. Beta 2 has 1 hydrogen and the CH3. Okay, so I'm just going to go ahead and draw the hydrogens in there for beta 1, and then draw the hydrogens for beta 2. So this was going to be 1 hydrogen here. So when I'm doing the elimination, I'm going to end up having a double bond here between alpha and beta 1, and a double bond here between alpha and beta 2. So my product here is going to be two alkenes. I'm going to form a double bond in here. Notice I'm losing the OH. So you're going to lose the alpha OH, and you're going to lose the beta 1 hydrogen. This is for the first one. I'm just going to keep the CH3. Plus, for the second one, you are losing still the alpha OH, and you're losing the beta 2 hydrogen. I'm just going to keep the CH3, and now my double bond is going to be over here. Now the question is, which one is major, which one is minor? So all what you need to do is, again, you're going to highlight the alkene in there. So again, in my product, I have no sign of OH anymore because I lost it and made an alkene. So I'm going to highlight my alkene in here and see how many carbons it's connected to. So that alkene is connected to 2 carbons. So this one is a disubstituted alkene. And this alkene here is connected to 3 carbons in there. So this one is a tri-substituted alkene. And remember the rule, the more substituted the alkene is, the major it is. So this one is going to be the major product, and this one is going to be the minor product, the minor alkene product. Okay. Let's have another example. Something like this. So let's say, for example, if I have an OH, if I have a CH3, and if I have an ethyl group over here. And we're doing the same thing. We're doing the dehydration, which is the H3PO4 at a very high temperature there. So as I said, just go ahead and locate your alpha carbon and now all the beta carbons around it. This one is an example of a tertiary alcohol. Okay, before this one here was an example of a secondary alcohol. So secondary alcohols normally they have 2 different beta hydrogens if the R's are different around the alcohol. Tertiary alcohols, if the R's are different around the alcohols, you're going to have 3 different beta hydrogens. So this is an example of 3 different beta hydrogens. I'm going to call this beta 1. And then this one is going to be beta 2. And don't forget that I do have over here, that is going to be beta 3. Because the definition for a beta carbon is the carbon that is connected to the alpha. So the one that is connected to the alpha is called beta. So I have 1, 2, and 3 of them in there. And all of them, they have hydrogens. So I'm going to start with beta 1 hydrogen. And then beta 2 hydrogen in here. I have 2 of them, but I'm just going to consider just 1. And beta 3 is a CH3. So here I have 3 of them. And again, I'm just going to consider only 1. So if I lose minus the alpha OH and minus beta 1 hydrogen, then my product, my first product here is going to have an alkene between the alpha and the beta 1. I'm going to keep the same substituents, you guys. So I do have a CH3 here. Just keep the same substituents. I have a CH3 on the alpha, keep it. I have an ethyl group on the beta 1, keep it in there. The only thing that you would need to take out is the water, the OH of the alpha and the beta 1 of the hydrogen. Plus, I can lose the alpha OH, and I can lose the beta 2 hydrogen. Okay, I'm going to keep the ethyl group. So now if I am losing here the OH and the hydrogen, then my double bond is going to be here. Still, my alkene is going to be in that same position. I'm not changing it. Plus, I can lose the beta, one of the beta 3 hydrogens in there, and the alpha OH. And minus beta 3 hydrogen here, there. I'm going to keep the ethyl. Now my double bond, notice where my double bond will be. My double bond will be here now. So my double bond will be outside the cycle in there. So that is going to be my double bond outside the cycle. I lost the alpha OH that was here and the beta hydrogen that was on beta carbon 3. So I'm going to end up over here having the CH2 in there. So which one is the most substituted alkane? Again, you are to locate your alkene and see the degree of substitution of each one of them. Let's go ahead and locate the carbons around the alkene. So around this alkene, I have 1, 2, 3, and 4. So this one is a tetra substituted alkene. Around this alkene, I have 1, 2, and 3 carbons. This one is a tri substituted alkene. And around this alkene, I have 2 carbons in there, which is a di. So definitely the tetra is going to be the major product. And the other two, these two over here, are going to be the minor products. Always you have one major and the others are going to be minor. Let's have another example here. This is again a tertiary alcohol, similar to the one that I just drew, but this one is a chain. So this one is a tertiary alcohol there. So I am going to locate my alpha carbon and then my beta carbon in there. And I do have beta 1, I do have beta 2 over here, and I do have beta 3. And all of these betas, they do have hydrogens in there. So I have hydrogen here, I do have hydrogens here, and I do have a hydrogen in there. Okay, so all of these hydrogens are different. You can see them. The CH2 is different than the CH3 is different than the CH. If your beta hydrogens are different, they're going to make different alkenes. If they are the same, they're going to make the same alkene. Okay, so let's go ahead and write all the alkenes that we are going to make. So the first alkene is going to be double bonds between the alpha and beta 1. If I take the alpha OH and the beta 1 hydrogen plus the second alkene, don't make sure that you take into consideration all the carbons in there that you have. I've missed a carbon over here. I've missed a carbon here. So make sure that you keep this carbon. This is a CH3. So we're going to keep that CH3 over here. I'm losing the alpha OH. And I will be losing the beta 3 hydrogen. So in this case, my double bond is here. Here you go. Plus, now we're going to lose the beta 2 hydrogen. Here you go. So I'm going to end up getting my alkene in there, and that is going to be my loss of alpha OH and minus beta 2 hydrogen here. And I'm going to end up getting my alkene. So let's go ahead and check which one is the most substituted. Okay, so highlight all of these alkenes in there and consider the degree of substitution of each. So this one is a tetra substituted alkene. This one here is going to be 1, 2, and 3. The number of carbons around the alkene, it's a tri. And this one here is a di. So definitely the tetra is going to be the major product. So this guy over here is going to be my major product. And the minors are going to be the tri and the di. So this one is going to be the minor, and that one is going to be the minor as well. Now, if I play with the temperature and I decrease it from 180 to 140, then in this case, this is still dehydration, but it's called dehydration at a low temperature. Now, dehydration at a low temperature does not give me an alkene. And this reaction is very limited because this reaction only works whenever I am reacting primary alcohols with each other and not secondary and not tertiary. The product is not going to be an alkene. The product is going to be an ether. So the reaction is going to proceed in this case where I am going to dehydrate two alcohol molecules. One alcohol is going to lose an OH and the other alcohol is going to lose a hydrogen. So at the end, I'm going to end up losing water. So this is why the reaction is still called dehydration, which is the loss of water. But now my product is not an alkane because of that temperature in there. It's not high enough to make an alkene, but it's high enough to lose water because it is above 100. And my product in this case, I'm just going to combine whatever is left. So over here, I do have the R that is left together with the OR in there that is left. I'm just going to combine them together and I'm going to form an ether. So dehydration forms two products based on the temperature, either an alkene if your temperature is 180 or an ether if your temperature is 140. Still the same reagent I'm using, which is sulfuric acid, but the only difference is the temperature in there. And if the temperature is present at low temperature, this means that I am reacting two alcohols together. I said that this reaction is limited, and it's limited only to primary alcohols. So if you have a secondary alcohol, there will be no reaction. Okay? So secondary, tertiary alcohols, there will be no reaction. And the alcohols can be primary. They can either be the same or they can be different. It really doesn't matter in this case. However, if they are different, the speed of the reaction is going to be slower, but the reaction is going to happen. So always do it like this. The first alcohol will lose the OH, and the second alcohol will lose the hydrogen, and then combine them together. So I am going to end up forming, see, the first alcohol has 1, 2, and the 3 carbons. So I'm just going to go ahead and draw those 3 carbons. This is how I draw it. I lost the OH. So that is going to be connected to the oxygen of the second alcohol. So I'm going to draw a bond in there and draw that oxygen. Okay, and then the rest of the second molecule in there, which is the 3 carbons. So I'm just going to go ahead and draw this 3 carbons in there. And that is going to be my ether product. Count your carbons at the end. I should not have more carbons in the product than what I started with. So I started with the 3 carbons on one side, 3 carbons on the other. So 3 carbons here and the 3 carbons there. That is a total of 6 carbons in there. Okay? This reaction happens because I am combining two primary alcohols together. You notice here that I am using 2 molecules of the same alcohol. So instead of writing it like this, there is another way to write it, which I can say I'm using excess of the alcohol. So if I write it like this, excess of the alcohol, meaning that I'm using 2 molecules of that alcohol, and then those same reagents, which is H2SO4 at 140 degrees, then the product is going to be condensing those 2 alcohols together, and I'm going to end up getting my ether product. Okay, guys, remember that the acid is very important in this reaction. So if there is no acid in there, there will be no reaction if the acid is not present. Okay, so pay attention to this. And when I use excess, this means that I'm using 2 molecules of the reactant. This is what I'm doing. I'm using 2 molecules of that. Instead of writing it like this, I can write it like this. And this over here is another way of writing this reaction. This reaction can also happen if the alcohols are different. Although the speed of the reaction is going to be slower, but it can happen as long as the alcohols are primary in there. And as I said, the first alcohol, no matter what alcohol is that, the first alcohol will lose the OH, the second one will lose the hydrogen, and then you are going to combine both together. So the first alcohol has 2 carbons, so we're just going to go ahead and draw the 2 carbons. And then draw the bond that we are going to do to connect it to the oxygen, because after all, our product is an ether. So we're going to have the second part of the alcohol, all of that. So this is going to be the oxygen there. And then that oxygen is connected to a CH2 and then a CH that is connected to 2 CH3s. Same number of carbons, pay attention. The only thing that I'm doing here is I made a new sigma bond between this carbon over here, the sp3 hybrid carbon, and the oxygen, the sp3 hybrid oxygen as well. There will be a new bond in there because of the loss of the water. Of course, I'm going to end up having water as a byproduct, but you don't even have to mention that. In these reactions, we only care about the organic product in there. So that is going to be my product. Please note that the first part of the ether, this represents the first alcohol. So this one represents the first alcohol. And the second part, including the oxygen. Okay, the second part including the oxygen in there. So that second part in there, it's going to represent the second alcohol. The first alcohol is going to lose the OH, so all what you need to do is put an OH in there to reach the first alcohol or to make the first alcohol, and then put a hydrogen next to the oxygen there in order to make the second alcohol. For this reaction, it won't happen because, as I said, at this very low temperature, in order to make ether, you need to combine 2 primary alcohols together, whether they are the same or different. The moment you have a secondary or a tertiary alcohol in there, so this one is a secondary alcohol, the reaction will not happen. So simply, all what you need to do is just write no reaction. NR means no reaction. And the reason why you don't have a reaction because you are using a secondary alcohol and not a primary alcohol.